All right, can you guys see my screen? Can you hear me, everybody?
Yeah.
Yes.
Yes.
All right, so we're going to talk about something called composition of functions today. And later, we'll see how to evaluate this type or these composition of functions. So as the name implies here, composition of functions is when you put two functions or more together. So basically what we do is we take two functions, let's say f, and maybe another function g. And basically we plug one function into the other. We take an entire function, put it in another one, and the result is what we call composition of function. This is the symbol f of g. F of g is the composition of f and g. The composition of. Okay, so that's the short answer. We just put two functions together, one into the other. We get something called the composition of the two. This is the symbol of it, f of g, or so this will read as f of g. Okay, the notation of the composition of two functions. To visualize it, think of it this way. Let's say this container was maybe some function f. Then we have another container like this, or another shape, that's g. So we plug the whole function g into f, okay, and the result is this composition here, this mix of the two functions. One goes into the other, so this is what we call f of g, okay? Or we can also call it f composite g. Okay, f of g, or you can say f composite g. So just a little illustration here, but we'll do examples with actual functions. Okay, so that's the whole idea of composition functions. Plug one into the other. So far we've done, for example, f of 1, we've done f of 2. That's when we plug a number into a function. Plug a number into a function and find some value. For example, if you have f of x, if f of x was 2x minus 1. What is f of 1 of this function? So if you plug 1 here and 1 here, it will be 2 times, substitute this one for 1 minus this one, and you simplify, you get 1. And you can also do can plug any number as we did before. We get a table, and once you get that table, we can turn it into that table into a function or a graph, as we learned last time. Okay, what is f of 2? F of 2 of this function. Everybody, how do you find f of 2?
Two times 2.
That's right. So we're going to plug 2 here and here. So it'll be 2 times 2 minus 1, which is 3. So this is what we call evaluations of functions. That's when you plug x and you get some y. So in this case, this is the y, this is the y. So evaluation of functions. Today we're going to do the same thing. We're going to plug something into the function. Instead of plugging a number like 1 or 2, we're going to take an entire function, for example, g here, and plug it into f. Okay, and let's see how to do that with actual functions. So finding composition functions. For that, we're going to need at least two functions. Let's say f of x, maybe 3x plus 2. Let's get another one, some other function. For example, 5x. Okay, f of x, g of x. First thing we want to find is, let's say, f of g. F of g, again, it just means the composition of f and g, meaning we plug g into f. Usually we use this notation here. This just means they have x in them. So f of g of x. F of g of x, again, does not mean multiply by x. It just means that's their variable. They both have the variable x in them. So we read it as f of g of x. Okay, that's how you read that notation. And to find it, again, it's pretty simple. F of g, which we can write like this, f of g. Just like here, for example, we say f of 1. We plug 1 into f. Here, we have f of g. F of g, we can also write it this way. So we're going to plug. The g goes into the f. Okay, so the g here goes into the f. And here is the most important part on how to find this composition. So we start with f. We're going to write it first. That's f. We're going to write it like this. So it's 3x plus 2. Okay, we're going to write f first, which is this. The only thing is you write it without the x. Just leave that x blank. So the x goes here. I don't want to write the x. Something else will be here instead of this x. So since we plug in g into f, that is f, we put it here. And inside that f, we're going to put the whole function g. This is g. It's given as 5x. That is it. That's the composition. Just like here, we put this into this. We got this mix. Same thing here. Just took g, put it into f, and we got this mix here. If you look at it, this is g of x, which we plugged into f. After that, we can say. I'm sorry, say it again.
Like 1, I was asking if it's a closed parentheses.
These here, just put parentheses for x.
Okay.
Okay. Now, once you get your composition, this is it. We may try to simplify it if possible. We can actually distribute this 3 times x, 5x, that's 15x, plus 2. And that's it. This is f composite g.
Is there another way of doing this?
This is the way so far. This is as clear, as simple as it can be. You just take one function and you plug it into the other one. Okay. The result is basically this. Trying to show every step. I don't want to jump from here to the last step, but that's how you find the composition of functions. That's f of g of x. Now let's find the other one, g of f of x. Let's say you have g of f of x. Again, we're just mixing or we're making the composition of 2 functions. In this case, which function goes into what? If you look at this example and over here, which function are we going to plug into what function?
G.
You're gonna put the
First
3x.
G.
You're
So
gonna put the 3x plus 2 into.
that's right. So we're going to put f into g. So g of f, which you can say as g of f. Okay, in this order. So g of f. Another way to write this notation is this, g of f, meaning this time. So again, the second one goes into the first one. So the f goes into g. Okay, g of f. So f goes into g. Which function do we write first again?
So you're gonna put
G.
The g, that's right. Always write the first one here that appears, the g. That's a g, but I'm gonna write it without the x. I'm just gonna leave the space for the x, leave it blank, so you can put something into it. So 5, and this is the x. Okay, what goes into the x now?
3x plus 2.
3x plus 2. 3x plus 2.
That's right. So the whole function f goes into g. So the whole f into g. This is g. And inside of it, we're going to put the whole function here, 3x plus 2. And that's it, okay? It's very simple. There's no nothing complex about it. Once you get it, that's your composition. At the end, you may want to simplify it a little bit. What do you do here to simplify this a little more?
Distribute.
That's right, 15x plus
10.
10, okay?
10.
And
Can we do one more time?
yep, we're still doing this. We're not done yet. We're going to do plenty of examples.
Okay.
Okay, just don't get ahead of yourselves and ahead of me, step by step. Okay, so this is our compositional function here, g of f, as you can see. It's different than f of g, okay? This is 15 plus 2, this is 15 plus 10. They're completely different, so make sure you respect the order here. F, g of f, so the second one goes into the first one, second one goes into the first one. And the result is just a regular function like every other function. So this is a first degree function. Okay, the graph is a straight line. The domain and range, as we learned the last time, are both negative infinity to positive infinity. Same with this one, it's also linear. Okay, this one is also a straight line. It has the same domain and the same range. Okay, so when you mix up two functions, the result is a new function. You can do a table of it, you can graph it, you can get the domain, range, a bunch of other things. As long as you have two functions, you can find the composition of the two functions. Okay, so let's do another one.
Is it okay if you write G parentheses FX parentheses?
Yeah, you can put the x here. That's fine. So let's take another couple of functions. Let's say h of x. Maybe let's say 3x to the second minus 4. And another function, let's call it k this time. This is just a name, a symbol as we saw with the notation. It could be any letter here. It's random, nothing important about it. And let's make this maybe x plus 1. Okay, first let's find, we're gonna write this notation first. How do you read this notation here?
H of k
Okay.
of x.
H of k of x, h of k of x. So which function goes into what function in this example?
K goes into H.
That's right, just gonna take k, put it into h. So it's h of k, in other words. It's probably more familiar, makes more sense as opposed to this one. Think of this as a number. If this was 1 or 2, you take the 1 and you plug it into h. Instead of a number, we plug a whole function. So which function do we write first again?
H of k.
Which function do we write first?
H.
H. So start with the first one, h. Let's write it down. I'm going to write it down without the x. Just going to leave the x blank here with 3. And this is the x, goes here, second power minus 4. Right, so you write your first function, and what goes now into this space?
X plus 1.
X plus 1.
That's right, the k. K into h. This is h, and inside of it, we're going to put k, which is given like this, as x plus 1. And that's it. That's your composition. You may simplify it. You can try to break this down. Okay, multiply this first, distribute, then multiply by 3, then combine them. But for now, that's not our subject. The important thing is that we get our composition. So that's the compositional function. Again, it's just a new function. It has its own domain, own graph. You can make a table out of it. You can do domain, range, and interval notations, whatever. By the way, what type of functions are these? What are their graphs?
Quadratic.
Quadratic.
Very good, quadratic. And how does graph look like?
Parabola.
That's right, parabola like this. The graph does not stop. What is the domain again of quadratic functions? The domain of all quadratic functions. See here, this extends, it doesn't stop, extends in both directions.
Oh,
Infinity, comma infinite.
Negative infinity and positive infinity.
Exactly. So quadratic function, as we saw, the domain is always this.
What happens, for example, then if like it doesn't have arrows and it has two closed dots, then the domain would change.
It changed. That means it does not extend. It stops right there.
Okay.
Okay. So the range depends. So the range depends on the graph. Maybe up, down, right, left. The domain is always this. So that's what we talked about last time. For linear functions, both the domain and range are always this. For quadratic, again, the domain is always this. You don't have to do any graph or do anything. You can write it right away if you're asked. The range will depend on the position of the graph on the bidimensional graph. Okay, so that's h of k of x. And again, once you have that composition, you may, if you want to graph it, you can graph it like we did last time. You can do anything you want. Whatever you do with a regular function, you can do with compositional function.
Can you go up for a second?
Like this?
Yes. The first one would be just a linear because it's exponent to 1, right?
Mm-hmm.
Okay.
Yeah, that's what we said earlier, both linear lines. So we did h of k. Now let's do the other way around, which is completely different. So this time I'm going to do k of h. So k of h of x. So again, it would be k of h. I'm going to write k first, which is here. So k is x plus 1. Okay, x here, plus 1. What goes inside the parentheses?
3x squared minus 4.
That's right. So inside of k, which is this, inside of the x, we're going to put the h. So h goes into k. H should be here. There's h. 3x to the second minus 4. And this is easier to simplify. We can combine the negative 4 and the 1. As opposed to this one, which is a lot of work to expand and combine. Probably you could leave it like this, but this one, easier to just combine these two. So it'll be 3x to the second minus 3. And again, it's different than the other one. So h of k, k of h are totally different. And it's another quadratic function. It's also like this. Okay, it's also as a parabola, the domain is going to be this. The range will depend on the position of the graph. And pretty much that's the whole idea of finding composition of functions. Plug one into the other. Very simple. There's nothing to it. Don't let this notation throw you off. It just means plug one into the other. That's all it means. This pretty much equivalent to this one. This symbol here, the letter circle, means the composition. If this was a dot, don't confuse that with this. This is a multiplication, okay? This is not the same as the letter circle here. This is a multiplication, as we did last time, u times f by g. But if you see this, it means composition. It means you gotta plug this into this, not multiply it like this, f times g. Okay, so we found composition functions. We can find them easily. Now let's see how to evaluate them. Let's see how to plug some number here instead of x. Let's see what happens when you have a number here, 1 or -2 or 3. That's what we call evaluating. This is finding, but the next one will be evaluating composition of functions. All right, so let's maybe work with the same ones here. I want to take these ones, h of x and k. All right, so you may see a question like this. So h of k of, instead of x, as we saw before, we may have a specific number, maybe 1. And we need to find that. So h of k of 1. The short answer here is 1 needs to go into this. Okay, just like we did with the regular, with 1 functions. See, 1 goes into f, 2 goes into f. Here, This is a function, okay? It's a function itself. So 1 goes into this function. So if you have this function already, that's good. You just plug 1 into it. Do we have the composition of these? Do we know it yet, the composition of these two? We do. We have it here. I mean, the first one, not this one. We have it here. That's h of k, which is this. So we can take the 1 and plug it into this composition, which is that. Okay, take 1, plug it into this, and you're done. Or if you don't have this yet, you don't have to find it first. It's the good news about when you have a value here, you don't actually have to find this composition. There's a way to do this without having to go through this step of finding the composition. And this is how you do it. 2 simple steps. First, you want to evaluate this. When you find k of 1. That's the first step. There's 2 steps. That's one of them. K of 1. How do you find k of 1 again?
You plug 1 where x is
Into what function? The k, right?
into the k function.
Into this. This one is a 1 here. You're going to plug 1 into k. This is k. So you're going to plug 1 here. K1 plus 1, which is 2. That's the first step. Now, so we found this. Whatever we get from here goes into h, which is this. So whatever this evaluation is, which is 2. So that 2 goes into the first function, h. So then h of 2.
So
This 2, this specific 2 goes here. Not 1 again. 1 for the first one. After that, the result of that goes into the other function. And we're almost done. We're just going to take 2, plug it into h. H is here, so make sure you use the appropriate
Yes.
function. 2 into h, so it would be 3 times. Substitute this with 2. The second minus 4. Okay, we're going to do the exponent first. So it'll be 3 times 4. Minus 4, which is 12 minus 4. That's 8. And that's basically our answer here. So h of k of 1 is 8. So this 8 is what answers the question. So we do it in 2 steps. Evaluate that first. Whatever you get from here goes into that. Okay, that makes sense?
yep.
Yes.
Okay, very simple. You just plug any value. We're going to do a couple more examples. Let's say, let's do another one with maybe q of h of, let's say this time maybe negative 2. Okay, q of h of negative 2. What do you find first?
h negative 2.
That's right. So you evaluate these two first. H of negative 2. That's your first step. And again, h of negative 2 meaning plug negative 2 into h. This is h, so we're going to plug the negative 2 here. So 3, negative 2 to the second. And minus 4. Again, simplify this. Start with the exponent first. So 3 times 4 minus 4, which is 8. All right, what is the next step?
K of 8.
A of h.
That's right, k of h. So we found this h of 2 is 8. So this is 8. It's going to go into the first one. So we're going to do k of 8. K is this one. So we're going to plug the 8 here, and here would be 8 plus 1. And that's it. So this is the number we're looking for is 9. Okay, so the evaluation is pretty simple. Again, you need to plug this into this. That's the case if you don't have the composition. So if you don't have the composition, you can do this in 2 steps. What if you had the composition of this already? You're just going to plug the negative 2 into that composition instead of plug in twice. You can do -2 into the composition if you have it. Do we have this composition, by the way?
Yes.
Yes, which is? What is K of H? Is here.
3x to the second minus 3.
That's right. We can just plug directly into this composition. Plug the -2 into this. And we get the K of H. Is 3x to the second. That's what we found earlier here. We can take that -2. Okay, this -2 here goes into the mix. Okay, so the -2 goes into the composition. This is the composition. So basically the 2 will be here. You can say 3. -2 to the second minus 3, and you should get the same result. So here, we used 2 steps, we got 9. But if you plug this into in 1 step into the composition itself, which we have, we should also get 9. If you don't get 9, there's something wrong. But you don't have to do it twice. You only have to do it once, either this way or that way. This is easier because you don't have to find the composition first. But if you already have the composition, it's probably easier to use it and plug once instead of doing this twice. So this will be, again, we do this first, so 3 times 4 minus 3, 12 minus 3, which is 9. You can see it's the same number here. We got 9 here. We also got 9 here. Either way will be fine when you evaluate. Okay, so we got 9 here, also 9 here, which is good. If you prefer to do it this way, you want to find the composition first, that's fine. You can find it and plug that into that. Or you may do it into simple steps like these. This can be convenient because you don't have to actually find the composition of the functions. Let's do a couple more. H of k, maybe of 2, or maybe of 3. Either by using the composition or without. Let's try to do this without using the composition. Let's assume we don't know it, even though we do have it here, H of k. But let's assume we don't have this, and we don't want to go through this. So probably the easy way is to just plug twice. Okay, what do you do again first to evaluate this? 2 steps. What's the first one?
Root of 3.
That's right. Let's evaluate the closest one to the number. Evaluate that. Whatever we get from here, whatever we get, we're going to plug into the H. So K of 3. Again, K is here. So we're going to plug 3 here. K of 3. 3 here will be 3 plus 1.
It's 3 plus 1.
Which is 4. And next step. What do we do with the 4 now?
H to the 4.
H, no.
H of
4.
4. That's right. I'm going to take the 4 here, plug it into the first one. So this is 4, plug it into H. 4 into H, again, make sure you use the right function. H, we're going to use this one this time, 3. I'm going to plug the 4 here and here. The 3, 4 to the second minus 4. And simplify this. Start with the exponent, so it will be 3 times 16 minus 1. This is 48. Take away 1, which is 47. Okay, so 47 is our answer here. Okay, and that's about it basically for composition functions.
Professor.
If you have x here, just 1 second. If you have x here, you have to plug the function into the function if there's an x, as we did earlier. If you have a specific number, then evaluate this first. Whatever you get goes into the first one. Yes, go ahead.
H is not 3x to the second minus 4.
Maybe. Is this a 4 here? Oh,
I
you're
see
right.
4.
That's
Yes.
right. should remain the same, okay? Should be the same function. This will be -4. That's right. It's got to be a -4 here. So the result will be what the result be 40, 44. Thank you for that. Good catch. Yeah, so that's basically how you evaluate your functions and how you find your compositional functions. But no big deal. Don't let the notation here confuse you. It just means plug. So if you have x again, if you have x, that means you have to plug one function into the other. So you got to find something like this with x in it. If you have a number here, that's probably easier. You don't have to find composition first, just evaluate. And your result will be a number instead of an expression like this. You will have a number. If you have a value, the result should be a value. If you have x here, the result will be most likely a function, an expression with x. It's like here, like here also. Okay.
Are you able to write like the rules just the same way how you did it when we were doing the
I'm sorry, say again?
I was asking if you could write rules for this.
Rules or maybe the order in which you go about.
Said write rules.
Yeah, if possible.
There's no rules basically. This is it. Just plug things into this. The rules are whatever we did with functions. You can graph these. You can do whatever you want with them. It's just function.
No, I don't mean like that. What I mean is, so if you have already, if there's an X and you know you're supposed to find X, or if there's no X and there's a number, then you know that you're plugging the number in or whatever. That's what I was referring to, but it's okay.
That's basically, so there is finding the composition, okay? And there is evaluating, okay? So again, finding is when you plug a function into the other, okay? So when you find a composition.
Move the page up just a little bit.
Okay, so again, when you have X here, that's when you find the composition. When you have X, you know that you gotta plug a function into the other. With the second part is evaluating. So you may say evaluate. So that's when you know if you have a value here, you need to evaluate. So that's when you plug twice. There's nothing else to it. Just literally this. And after this, whatever you get, the result, when you make the composition of the two functions, what you get here is just a regular function. Like I said before, you can, all the rules we did with the functions before apply to them. You can graph them, get the domain, range, make a table, a bunch of other things. Okay, and that's pretty much it for the compositions. Any other questions, everybody?
No.
Everybody else? So this is related to what we started last time, the function notation, how to plug, for example, how to do these here, how to plug, and the graphs and the domain and range. We talked about that extensively in the past couple of lectures. So you're sure you get the previous two before you can understand this. This is based on that. And this is not a lot of things here, just a couple of things. Plug a function or plug a number, that's all. And so basically just this is meant to save time. Let's say you have two functions or more, let's say f, g of k. So instead of plug in here and plug in here twice, whatever, basically we mix all these together into one function. Let's call it, for example, k. So instead of doing the work twice or three times on each function, you just mix them up, put them into one. So instead of plugging 3, you just do that work once on the composition of the 3. This is the concept of the reason we use these composite functions. You just like you say you want to carry this shape, and maybe inside of it there's maybe another shape. Let's say, so let's say you have this container, you want to carry this and carry this other container that looks like this, and then maybe some other shape. So let's say you want to move these from point A to point B, right? So do you want to move one by one at a time? Or this one go from A to B, come back, do the same thing with this shape, and then come back and do this? Or do you want to make a composition with the two and just do it once? Which one seems convenient? Which one would you do? Would you carry one by one, for example, from A to B? Or would you make a composition of the three and just carry the result here once? Which method is seems easier, one or two? Think about carrying physical stuff. You want to carry like some physical stuff. So the second one seems easy, right? Second one, basically just mix things up. Put this container into this and this one into that. So you just have a mix here. So this is the composition. So it's easier to do this once. So you can carry the whole thing together from A to B instead of carrying this one, coming back and doing this. This is a little concept of the reason why we use compositional functions. So we avoid repeating, doing the same thing again. Okay, I'll give you a couple of problems to do on your own now, just like this.
Should be fun.
It will be.